Okay. Welcome everybody to this new session of the Euclidean probability seminar. We have the pleasure to have with us Manuel Lladser from University of Colorado. We discuss about something about metric spaces.
All right, so nice to see you. Hola. I am a former student here, so it's a lot of fun to be back. Very nostalgic, actually. But I'm happy to see a lot of new faces and see how the department keeps growing and bringing new people. So I will be talking about three concepts: the concept of metric space, the concept of Jaccard metric, and the concept of resolvability of a metric space. And to start, I want you to remember something that you probably know since you were babies, that when you have a flat space, if you select 3 points at random, in this case, the blue landmarks, that are non-collinear, then any other point in the space is uniquely described by its distance to those landmarks. So in other words, this vector of distance, d1, d2, d3, acts as a one-to-one correspondence with the plane. Of course, we know the plane is two-dimensional, but without knowing or having the concept of Euclidean dimension, we could say that in this regard, the plane is three-dimensional, but it's not two-dimensional in this regard, because if you only select 2 points, there are infinite points that are at exactly equal distances, but they are different, okay? So that means that if I select another point, like the yellow point over here, it will have its own sets of distances, meaning at least one of these 3 distances has to be different between the red and the blue point. All right, well, but if you look at this picture, there is nothing special about the Euclidean plane, except that I need 3 points to play the game, meaning to trilaterate the plane, okay? Now, a clarification. I'm using the term trilateration rather than triangulation. Triangulation is based on angles. Lateration is based on distance, okay? So that's the distinction between the two terms. All right, so, but there are a lot of very interesting metric spaces with very weird shapes, with very weird forms on matrix. And the question is, can we generalize the idea that happens in the plane? And the answer is yes. We are going to say that one resolves the space or any space when I can play the same game that I already play in the plane, but I'm in that space under whatever is the metric that I put in that space. Okay. Now, by a metric, I mean it's non-negative, it's symmetric, and it satisfies the triangular inequality. But in an arbitrary space, I may need more than 3 points to do the game. So rather than doing a trilateration, we're going to do a multilateration. Is the concept clear? Concept of multilateration as a generalization of trilateration.
But it's a fixed number? It's a fixed size of?
No, every space will have its own number of points.
Right, but for a single space, it's one given number.
Yes. Yes.
Fine.
Hopefully. Hopefully it's fine. All right, so let's.
I mean, if it's infinite, then it's always solvable, no? No, because if you have all the points, you have 1 point.
Well, if it's finite, the space, the whole space can be used to multilaterate.
Yes.
But if it's infinite, it's not clear if there is a finite
set
so that's what that multilaterates.
Resolvability is the finite, the existence of a finite set.
No, the existence of some sets that plays that game, but now we'll give it in a more mathematical sense. Okay, so I will focus on finite metric spaces precisely because they are actually very non-trivial. They are discrete, complex objects, can be described by finite metric spaces. So XD is a finite metric space. A subset R1 up to Rk, is said to resolve the space. And of course, that depends on the space X and the metric that I'm using there. When this transformation that gets every point in the space and associates this vector of distance to landmark 1, to landmark 2, to landmark k, when that transformation is 1-to-1 or injective. Yeah. So one can think of R1 up to Rk as landmarks with the property that in order to resolve the space, each point in X is uniquely defined by its distance to those landmarks. Okay. Now, what is pretty about this, and I want to come back to this picture, that if 2 points, here I'm using the Euclidean distance, if 2 points are close by in Euclidean distance, their distances must also be very similar to each landmark. Yeah? So the resolving set provides a way to encode information about the space in a way that similar points in the original metric have similar encodings. And that seems like a good property to have. Yeah? It's kind of a social security number or a root in Chile, your root. But the roots don't have that property. Our roots may be very similar, but we have no properties in common except being probabilists. Yes?
Age.
At age. No, it's much younger than me.
When they're similar.
Well, yeah, if you were registered at birth.
Well, of course. Which is the case now.
Yeah.
I didn't use it.
So, to me, that says this object is worth studying then, because it's like a nice encoding of the information. So, in mathematical terms, what you can say is that the infinity norm of the embedding of a point X with respect to the embedding of a point Y is at most the actual distance between those points. Yes? So mathematically, this distance is small. Those two encodings or representation must be very similar coordinate-wise. Yes? And those of you that are into the machine learning fever, that means that this encoding creates a nice feature to represent that space. Something you want to do in machine learning. So that's the point in red. Points close by in X are represented by vectors with similar coordinates. Yeah. Sorry, this D should be a K in Rk because I'm assuming I need K points to resolve. All right. Well, what can we do to resolve a space? Well, you can always use the whole space to resolve it. I'm the only point at distance 0 of myself. I immediately know who I am if I am part of the resolving set. So what is interesting is not finding a resolving set, is finding the smallest possible resolving set. And in a finite metric space, that number is a finite number, always. So we are going to define the metric dimension of the metric space as the size, so the absolute value denotes size, of the smallest resolving set. Now, a comment. This set doesn't need to be unique. You can have two resolving sets that are both of the smallest possible size. Okay? All right. Well, in an arbitrary metric space, finding this minimum is a difficult problem. It falls in the class of non-polynomial deterministic problems. It's very difficult to solve this problem. There is no known polynomial algorithm to do it. All right? So if I give you a metric space to resolve it with what we know, the best you can do is to try to resolve it optimally. And there is a greedy strategy called the information content heuristic, which I will keep calling later ICH, that greedily does the following. It computes the distance matrix of the space. So every pair of points, what is distance? It's a symmetric matrix. And then it starts to choose a column maximizing the accumulated entropy of the columns you already chose and the column you want to add. It's trying to maximize that entropy. Now, when that entropy hits the log in base 2 of the logarithm, you know that you maximize entropy, meaning that every point is in a single class, and you now have resolved the space. Well, it's a very expensive algorithm. It has order cubic in the size of the metric space. That's super expensive. But it has some theoretical guarantees, which is the size of the resolving set given by the ICH is at most this multiple of the true metric dimension of that space. And this bound is theoretically optimal for, I don't remember, all possible greedy algorithms or something like that. You cannot do better than that for a greedy algorithm. Okay, so far I told you the concept of metric dimension, not dimension, metric, the number of landmarks, the concept of resolvability, and an algorithm that is super expensive to find a resolving set. Okay, so let's put the concept in practice. The concept of metric dimension or resolvability originated in graph theory first. People were not thinking in terms of metric spaces. But a graph can be thought as a metric space where the nodes of the graph are the elements of the space, and the distance between two nodes is the shortest path distance. So the distance between 1 and 4 is 1 because one edge connects them, and the distance between 1 and 3 is 2 because two edges connect them. Yeah? Now, thinking of that as my metric space, I can ask how many nodes do I need to select to resolve it? Well, you can convince yourself that no single node resolves it. For instance, node 1 cannot resolve it because 2 and 4 are at distance 1 from 1. Node 5 cannot resolve it because nodes 3 and 1 are at distance 2 from 5. And you can play that game with every node. So no node resolves, single node resolves. But these two nodes, 1 and 3, resolve that graph. Why? Because if at every node you compute the distance to 1 and to 3, you're going to get these vectors 0, 2, 1, 1, 2, 0, 1, 2, 2, 2, 3, 1. And none of those two vectors are the same. Yeah? So we can say that because no single node resolves it, but two nodes do resolve it, the metric dimension of this graph is 2. Everybody got that? All right. All right. Well, having started in graph theory, at the level of graphs, the concept of metric dimension has a huge history. Huge. Okay? It's a tremendous literature. Not only that, if you subscribe to that keyword on arXiv, you get every day a new paper that is solving some metric dimension or resolving set in some graph. So I wanted to tell you a few things. Assuming that the graphs are connected and undirected with n vertices, the only way a graph can have metric dimension 1 is if it's a path, a linear graph. The only way it can have metric dimension n minus 1 is if it is the complete graph on n vertices. Every node is connected to every other node. And there is an algorithm that tells you how to find a resolving set and the metric dimension of a graph that is not a path and is the number of leaves minus something called a major exterior vertex. What is that? It's a definition. You count those nodes, and if you subtract that from the leaves, you know exactly the metric dimension, and then you also know a resolving set of the tree. As you can imagine, there are many classes of trees that, how do you say, many classes of graphs whose metric dimension is known. Yeah. And it's a very cool concept. Okay, I don't want to advertise it, but sometimes you remove one edge from a graph and the metric dimension can change tremendously. Because when you remove one edge, you may be destroying many shortest paths. And the metric dimension jumps to a totally different quantity. Okay? So I think it's very interesting. Now, at the level of metric spaces, the notion of metric dimension and resolvability is practically or comparatively unexplored. So there are a few more results, but I wanted just to give you a flavor. So if the space is complete, convex, and every pair of different points resolves it, guess what? That metric space is R with the Euclidean distance. That's it. There is no other possibility. If X is an affine subspace of the Euclidean space, then the metric dimension of the induced norm is the dimension of the space plus 1. So why did the plane have metric dimension 3? Because it has Euclidean dimension 2. You add another 1, you get metric dimension 3. Yeah. Which is not to say that any 3 points resolve it. Yes? It means it's possible to resolve it with 3 points. All right? And the last thing is that if this is the geodesic distance in the n-dimensional sphere, the metric dimension of that space is n plus 1. Okay, so the two-dimensional sphere has also metric dimension 3. Right?
And for other norms, like for LP norm, this is also the same for the second point?
I don't know. My interest has always been on the discrete spaces, but I don't know. I just know that some of these questions are really tricky. Because you need to show that certain nonlinear system of equation has no solution, but you add a new special point and suddenly there is a solution. Yeah, so it can be very tricky. Yeah.
And the first one, is it true for R2, say? 3 different points?
Oh, the first bullet?
Yes.
I don't remember having read that result. I think all of this comes from the same paper. I think there's one paper where all of these results come from. I don't remember that result in particular. Yeah. Without making more advertisement, I really love the discrete setting because you have so little tools, you know, like to grab the problem. Okay, so let me give you something more original. I don't know how much biology you know, but basic chemistry, an octapeptide is a sequence of 8 amino acids. It's a protein. Okay, it's a protein composed by 8 amino acids, but you can think of it as a sequence of numbers. Yeah. There are 20 amino acids. So how many octapeptides are there? 8 to the 20 in principle. Yes, I'm not saying they exist in nature, all of them, but they're 8 to the 20. And how can I represent an octapeptide numerically so that a computer can understand it? You could create a binary matrix where the rows represent one of 8 positions and the columns represent the amino acid at each of those positions. So that means you need 160 dimensions to represent naturally an octapeptide. Is that clear? Multiplicative principle. Yeah. Okay, 160 dimensions. Now let's compare two octapeptides. For instance, these two by their Hamming distance. What is their Hamming distance? It's the positions at which they differ. So this octapeptide and that octapeptide are off by the last amino acid, so their Hamming distance is 1. And you can prove that that's a true metric in the space of octapeptides. Yeah. But there are many octapeptides. There are 25 billion possible octapeptides. By the way, I was trying to think what is something you can estimate how large 25 billion is. So that's more than 10 billions, which is 10 to the 10. And I read somewhere that the number of years since the Big Bang, years, Earth years, is 10 to the 10, more than 10 to the 10. So it's a lot, it's a huge space, yeah? And if you think about it, if I want to apply the ICH, I need to construct first a distance matrix of 10 to the 10 or 25 billion by 25 billion. Compute all those Hamming distances, and then start computing joint entropies. It's expensive. But with some student, we figured out a way to multilaterate the space. And we use a randomized algorithm, and then we use something, I don't know how much you know, called Grosvenor basis to verify that the solution the randomized algorithm gave us was correct. And we determined that these 77 octapeptides, 7 rows and 11 columns, is a set, so are enough to resolve that space with respect to the Hamming distance. Okay. Now, what is the point?
One question. When you have this, how do you, I mean, if I give you the numbers, is there an easy way to get the right amino acid?
I think so, yes. There is a way we can tell you which amino acid is at those distances. Yeah, I agree. But look at the natural encoding needs 160 dimensions, but it's very sparse. Most of the entries are 0. But with this distance, you just need 77 dimensions. So it's about half the dimensions are needed. Yeah. So that's the point I want to make, that the concept of metric dimension of a metric space can really make you think about certain problems very differently. Yeah. All right. So that's an example I wanted to give you before I go into the topic of this.
Sorry, Manuel, I missed something basic. But
yeah.
Why is it sparse?
Oh, because there are 8 positions and 20 possible amino acids on that position. So if I give you one protein, every row has a single one, and everything else is 0.
It's very sparse.
Yeah. So now this one is not sparse because that would be a lot of non-zero distances. Yeah. Okay. So
probabilistic or
we use a probabilistic algorithm that told us with high probability, I think these 83 landmarks resolve. And then we use a deterministic algorithm to throw away landmarks that were not needed, but keeping landmarks that are really needed. So deterministically, we know these results. There is no, yeah, that resolves.
But there could be a smaller one.
There could be a smaller one. Yeah. But I don't know what is the metric dimension. I know asymptotically, but not for a finite size. Yeah. Okay, so now hopefully you see how versatile is the concept. Now let's focus on a specific metric space for the rest of the talk, the Jaccard metric space. So we're going to consider a finite or empty set capital X, and we're going to consider the power set of X 2 to the X. Those are all possible subsets of X. And 2 to the X is a nice notation because it's like the functions from X to 0, 1. Yeah. Now the Jaccard distance, this is a very old distance introduced by a botanist, by the way, not a mathematician, says that if I give you 2 sets, the Jaccard distance is 0 if they're equal, and it is the cardinality of their symmetric difference divided by the cardinality of their union if they are different. Okay. So on a picture, think of So here is A, here is B. You are looking at how many points are there divided or relative to how many points are here. That's the Jaccard distance. Now, why we were interested in this space and in this distance? Well, tweets. We were interested in analyzing tweets without using machine learning.
That's the X?
Yeah, so the X is the vocabulary people are using. Okay, the words in natural language processing are the tokens, which are kind of roots of a representative word. And we wanted to do a lexicon analysis, meaning we were not doing a, how do you call it, paying attention to grammar, punctuation, none of that. We wanted to know what are the words, terms somebody's using to describe a situation. So that's a lexicon-based question in natural language processing. Because you lose grammar, yeah? And when you work in this setting, you don't think of the power set of X, you think of bags of words. That's the way the computer scientists like to think about it. Just words in a bag. There is no order, no noun, nothing. So that was the motivation. And the question is, the natural question is, can we find non-trivial subsets that resolve it? I mean, it's a finite space. So there's always a resolving set. And what's the metric dimension of this space with respect to the Jaccard distance? That's the questions we are going to try to address today.
Just one question. So here you're assuming that every possible combination of
Words.
letters is
Of words.
okay.
Words. So, hey,
Okay.
hi, good morning. The bag of words has hi, comma, good, comma, morning.
Okay.
Yeah. All right.
Every sentence is done.
Yeah, there is no sentence order. I could have said hi, good morning, or good morning, hi. Yeah. No, we are not. That's why it's called lexicon based. I just want to know the concepts you're using, not the precise information you're trying to transmit.
And you say twice the same word, it counts once.
Yes, it's a set. So repetitions don't matter. Order doesn't matter. So if I give you X is 1, 2, 3, 4, or it could be words, you can construct the matrix of Jaccard distances between all its possible 2 to the 4 subsets, 2 to the 4 by 2 to the 4, and you need to select the minimum number of columns that make the rows different along those columns. Now, using the ICH algorithm, that expensive algorithm, we determine that these 3 columns suffice, okay? So if I give you the 1, 4 is the only bag of words with cardinality 2 that is a distance to third, 1 and 1/3 of these 3 landmarks, yeah? So this space, I can at least trilaterate it when X is 1, 2, 3, 4, yeah? Okay. But I told you that the ICH, the complexity is the space cardinality to the cube. Well, my space is 2 to the X to the cube. Is 8 to the X. You rapidly run out of computational power to use the ICH. Yes. So that made the problem very non-trivial for us, because we could barely do experiments to try to understand how to resolve this space. Okay. So the first thing we figured out was that if you have a resolving set, it must have 2 properties necessarily. First, it must separate different points, meaning if I give you 2 points in X, one of the landmarks are subsets of X, must contain one of the points, but not the other. So it has to separate the points. And it also covers or almost covers the whole space, meaning the union of all the landmarks. Again, a landmark is a point. A point here is a subset of X. Yes, so those are the points in my space, subsets of X. So the union of all those subsets has to be the whole space, or the whole space, but 1 element. You cannot be missing 2 elements. You are automatically not resolving. Yeah. Now, we found sets that have these two properties but are not resolving. So that means these are necessary but not sufficient. All right, so that's basic properties. Surprisingly, this wasn't ever very useful. I thought it would be a useful property, but it wasn't. I don't know why. Maybe I don't know how to squeeze it. Okay, so the first thing we found out, and I will give you only two proofs, is that if R resolves 2 to the x, it must have at least this cardinality. And if you look at the leading term in the numerator and the leading term in the denominator, that means that it must have at least size ln of 2 times the size of x divided by ln of half the size of x. That's with lesser, you cannot resolve. Now, what is the key idea? So let's try to understand. So we're going to choose this number k, which is the floor of half of the size of x. And we're going to assume that R resolves 2 to the x. What does that mean? Let's remember that this vector of distances to the elements in R is a one-to-one function. That's the definition of being resolved. Now, suppose that A has cardinality k. It's a subset of x of cardinality k. Then the Jaccard distance, if you use the inclusion-exclusion formula in the denominator, is the same as the cardinality of A plus the cardinality of R minus the cardinality of A intersection R. And here I will denote intersection putting the two sets together. Okay, so when I write AB, what I mean is A intersection B. Okay. And you can play the same game with the numerator, which is the symmetric difference. So this is the formula for the Jaccard distance between A and R when A has cardinality k. But when you look at this, you realize that the number AR is either empty because AR is either the empty set or is all of A. So this quantity can only live between 0 and k. So that means that this distance is a function of a quantity that has only k plus 1 possible values, which means this distance can at most have k plus 1 values, nothing else. But the set R has this many elements. So that means that the range of this space has at most this cardinality, k plus 1 to the cardinality of R. And in order to resolve, I must have at least as many vectors as sets of cardinality k. If I have less, there's a collision by pigeonhole principle. So that tells you that the cardinality of R is at least the logarithm of this space divided by the logarithm of k plus 1. And if you work, this is standard work, Stirling formula, things like that, you arrive that the cardinality of R is at least x over ln of x. But if you are precise, if you pay attention to the details, you make it to that inequality. So that's the least number of landmarks or subsets of x I need to resolve it with the Jaccard distance. Is the result kind of clear? Yeah. Now, I want to make a comment. You could ask me, why did I choose k this? I didn't know what k to choose. Eventually, we realized that later we found an upper bound that was of the same order. So then we knew, okay, we're going to choose the k that give us that order. Okay. But at this point, any k works, and each k gives you a different lower bound. So you should maximize this in k to get the best bound. Okay. All right. So I know the metric dimension has to be at least this quantity, but how large is it going to be? And that's where we're going to spend the rest of the discussion today. So this is something we realized at the very end of this research, which is if you give me two sets of different cardinality, then these three landmarks So these three landmarks resolve any pair of subsets of X of different cardinality. You hear that? Now, this was to me heartbreaking because from the point of view of the application, it's not an interesting result. So how can I resolve two sets of different cardinality? Pick up the empty set, pick up a singleton, and pick up the complement of the singleton. That X is fixed. Then the Jaccard distance to one of this set has to be different from the Jaccard distance to the same set by A or B. So this is saying that to distinguish subsets of X of different cardinality, it suffices to know if they contain an special word or if they don't contain it. And therefore, there is not much information in the encoding that I was telling you at the beginning. Yeah, from this point of view. And I will come back to this nuisance later because it motivated us to study one more thing in the end. Okay, so I know how to resolve pairs of subset of different size. I know how to do that. But I already know that I need this many landmarks. So this trick has to be a bit more elaborated to resolve pairs of the same size. Something I have to think differently about this problem. So we did some simulations. So we consider x's of size between 1 and 14. Using the ICH, we found a resolving set. So if x has size 14, that is a resolving set of size 8. And then we look at the average size of the landmarks. Remember, landmarks are subsets of X in this space. And we plot them. Looks very diagonal, so let's draw the diagonal. And like, okay, if I had a minute to make a decision, I will say that typically a landmark average is 1/2 the space size. Okay, so landmarks are big. Half of the words are in the landmark, half are not. In average, some of them are much larger, some of them are much smaller. Okay. And this is, we couldn't do 15, 16, 17. We didn't have enough computer power to do it. So we had that. We tried 3 million things, nothing worked. And that's when I decided, let's try something more probabilistic. I mean, I'm a probabilist at the end of the day. Yeah. Let's think of this problem as a probabilistic problem. Okay, so we introduce this notion, a binomial x, 1/2. X is a set, 1/2 is a probability. What does it mean? It's a random subset that every point in the space belongs to it with probability 1/2. But for different points, those events are independent from each other. Yeah. Now, why did we do this choice? Because the average size of this set is 1/2 of the space. Yeah, that's why we did this. So using a probabilistic method that I will explain in a second, we were able to show that if you pick up K, ID binomial x 1/2, as long as K is large enough, we can show that this set that contains empty singleton, complement of singleton, and all these binomial sets resolves the whole space with high probability, meaning the probability tends to 1 as the size of the space tends to infinity. Yeah?
Stupid question. So the empty set, why do you need it? So the distance to everything that is not empty is 1, no?
Yeah.
So and to the empty, how much it is?
Well, the empty set is a distance 0 from itself.
Yes.
And it's a distance 1 from everything else.
And why it is giving us information? Why do you
what
need
was the reason? I think I needed it in part of the proof here. I needed to simplify my life saying, oh, because clearly A cannot be empty. A or B is not empty because otherwise one of those distances would be 1. And then I can reduce everything to leading with these two special landmarks. I think it's a technical reason, not an intuitive reason. Yeah? Okay. All right. So, well, you could say if you cannot prove it deterministically, how the heck are you going to prove it probabilistically? Well, actually, if this is for the masters, PhDs, there is something called the probabilistic method that helps you to show existence of complicated objects, just showing that the probability that the object arises is positive, or the probability that it doesn't arise is strictly less than 1. Yeah? So let me tell you how we arrive to that. Now, one more comment. If we put the lower bound we discussed already, using a combinatorial argument, with the upper bound given by the probabilistic method, we get that the metric dimension is of order x over ln of x. So it's sub-exponential on the number of words of reference. Yeah, sub-exponential. But it's not the best, because if you divide the upper bound by the lower bound, you roughly get a factor of 5. So there's a range that I wasn't able to close that gap. Okay. All right. We call this picture. Because of this picture, we decided to look at sets that flip a coin at every point in X to decide if they are in the landmark or not. Now, we could have chosen a p larger than 1/2 or less than 1/2, but there is a nice symmetry when you choose p equals 1/2. That simplifies a lot of the argument. So that's why also, for technical reasons, I like that distribution. Okay. So one of the problems that this problem creates is that when you compare two Jaccard distances, you're comparing two fractions. Hence, relative primes are part of the picture. And I don't know about you, but every time there's a prime involved in the argument, my knees tremble a little. I'm like, oh no, I have to use those ugly functions. Sorry if one of you is a numerical theorist, but that doesn't come very natural to me, okay? So I was trying to avoid at all costs number theory in the argument, at all costs. And one day we realized that if you have a collision, this is a collision, or A and B are equidistant from R, then we can say that the R, thought as a binary vector, because you can represent subsets of X as binary vectors, is orthogonal to a vector Z. What is the vector Z? Is the size of R plus B, vector A, minus the size of R plus A, vector B. So that's a vector. Some numbers here are non-negative integers. Some numbers here are negative integers. Okay. So it makes sense when I say think of a set as a vector. Yeah. If X is in the set, you put a 1. If X is not in the set, you put a 0, and you do that for every element in the space. Yeah.
That's not if and only if, no, it's just an if.
It's if and only if I request that R is not empty. Yeah, but I'm not interested today on the reverse. Yeah. Okay, so why do I like this? Because I know properties of inner products. That's the inner product between R and Z. And it's not number theory, it's geometry. Yeah, that's why I like it. So, but there's something very useful. When A and B have the same cardinality, this is a scalar that I can factor out. So when I do RZ, it's the same as doing some scalar times A minus B. Yeah? But when you look at A minus B as a vector, everything that A have in common vanishes, becomes a 0. So the only coordinates here that do not vanish are the coordinates that are in A but not in B, minus the coordinates that are in B but not in A. Those are the only coordinates And why I'm interested in that, because to say that RC is 0 is the same as to say that R times the special vector is 0, but this divides the problem into R's multiplying some ones and other points in R multiplying some negative ones. So what is showing up is a binomial. A binomial, this inner product is the difference of two binomials. That's what I want to say. Okay. Yeah. Oh, okay. Well, I'm very familiar with the binomial. I know many properties of the binomial. Maybe that will help me. Well, let's see if it helps. Okay, so now we'll explain the probabilistic method. So I will pick up K, ID binomials x1/2. I will define R to be that set. And I want to compute the probability that R does not resolve every pair of points. Okay. Well, that probability, because not resolving means there is a collision, yes, but I know how to resolve sets of the same size, different size, so I will assume they have the same size, yeah, is at most the probability that this happens, that R is orthogonal to this special vector C, but for every R in my resolving set. Now here's where the probabilistic method comes up. I want to show that this probability is less than 1. Because if I show the event has probability less than 1, there has to be at least one R that resolves. Yes? Everybody? Okay. But I want to show more. I want to show that as X becomes larger and larger, this probability becomes smaller and smaller. So I want to show that this probability sigma tends to 0. Yeah? Because that will show me a randomized way to construct a resolving set with high probability. Okay. Now, if you look at this vector, every coordinate is either a 0, a +1, or a -1. Because A and B have the same cardinality, there are as many ones as -1s. So the sum of the entries are 0. But because the sets are different, there has to be at least one 1 and at least one -1. So the sum of the absolute values is at least 2. Yeah? Now, computing this probability exactly is not easy. I don't know how to do it. So I will resort to the triangular inequality for probabilities. Yeah, sigma additivity. Or subadditivity. Well, okay. So the probability that R does not resolve is at most the probability that for some C, all these inner products are 0, which is what that is saying in a different notation. But I want to say something, and this was funny to me. For a while, I didn't know if the inner product notation mattered. But here is where I realized it matters a lot. It matters a lot because, why does it matter? I know this, I know it. It matters a lot. Because if I use triangular inequality here, I need to consider all possible A's and all possible B's that are different from A. That's a large double sum. But here, everything reduces to a single object. It's a single sum of terms in Z. So the number of terms that I need to adapt is a lot smaller if I work with this object Z than if I work with all possible pairs A and B. So that's a technical situation. So RC equals 0 means that where C takes the value 1 is balanced where C which takes the value 0, -1 when you intersect with R. So that's a probability that two independent binomials take the same value. Yeah. Now I here is the number of places where C has the value 1. So binomial I1/2 is the number of ones, and binomial minus binomial I, 1/2 is the number of negative ones. Yeah? But I have k independent events, so I take to the power k. Here are all the ways in which I can construct a vector in Z. All right, we have this sum. By the probability that two independent binomials take the same value, you can compute exactly, is exactly that quantity. You can try it. And that was a reason why I needed to consider I equals 1 different than I larger than 1. So let's not talk about that. But using Stirling formula, we arrived to the conclusion that this sum was at most this quantity. And the question was how to handle this sum, for which I was very glad to have taken Cal 1 at University of Chile, because they gave us hard problems like that. And then we realized that if we choose k sufficiently large, larger than this, then this quantity is bounded uniformly in the range of the sum. But if this quantity is bounded, asymptotically, this is the harmonic series grows logarithmically log of x divided by pi to the k over 2. And for that choice of k, we can also guarantee that that tends to 0.
So what happens if you, instead of 1/2, you get p? Or you...
Well, you don't get a nice formula. You'll get an expression that is a sum, and I need to start considering small I, large I.
And if you just graph it, do you get a better story, or
uh,
can you get? Is it optimistic? You can just put it on a graph.
I will be honest, I never did it. I was so frustrated with the problem. I knew 1/2 was making my life easier. I went for it. Yeah. In that case, I was a true engineer. Like, I want to understand the order, no matter what. Yeah. Now, summarizing, this proves this asymptotic order, tells you a randomized way to construct the resolving set. We use it to analyze some tweets, but today I didn't have time to add that to the talk. But I was so upset about, this only resolves sets of different size. So why I was upset, when I read this, it took me a while to write the sentence. So these R resolves back-to-words of different size solely based on the presence or absence of a single token, which seems too coarse for NLP applications. So I felt like, I wouldn't believe the encoding I will get will do a good job. So in America, I would say tweets that have the word Biden and tweets that have no word Biden. That's my classifier. I'm talking about, I don't know, Chile. I don't know if Biden matters or no Biden matters so much for Chile. So there's no useful information there. In here, if you write Talca, tweets that have the word Talca versus never use the word Talca. I don't know why that will give me any useful encoding. Yes. But I realized, okay, but I need this to separate all words, all backs of words of a different size, but arbitrarily different. What if I truncate that? And that's when I realized this, that if I look at my random landmarks and their complements together, then as long as k is order square root of x, so it's much smaller because I don't want to resolve all possible pairs, then I can resolve all pairs of subsets of size at most this. Order square root of x over ln of x. So I don't know, a tweet has how many characters? I don't remember, 216. Okay, then you compute the average word size. So you know, on average, a tweet has, I will make a thing, 24 words on average, no more. Yeah. So I don't need to resolve tweets of arbitrary large number of words. I just need to say I want this to be at least 24. And that's where we said, okay, this may be useful for analyzing tweets. Okay. So that's it. My former student, Alex, he was a master's student. Masters can do cool stuff. And my grant. And if you want to access the preprint, the QR code is there. Thank you, guys.
So thank you very much. So are there any questions? I have a thing. So how you try to look at it as a random graphs? Let's say,
Yeah,
I don't know, Erdős-Renyi graphs. How many?
it's done. Bolobas has a very detailed analysis of the metric dimension of Erdős-Renyi, almost for all the range between 0 and 1. Almost. 0 is boring and 1 is boring. But you can get to 0. He found the rate, how much you can get close to 0, how fast you can get close to 1 to still say interesting things. And the behavior is very interesting because there is a function, there is a scaling limit that uses a function, a continuous function evaluated at the floor of, let's say, 1 over p, something like that. So it looks continuous jumps, continuous jumps, continuous jumps. So it's a very pretty behavior on Erdős-Renyi.
I don't know if it's a question. It's more. You said it in your theorem, but you proved more than the order that I mentioned, which is the fact that if you choose randomly that order, then you will get
a resolving set.
So that's probably not. That's not true for any graph, I guess.
No, but this is only true for the Jaccard space.
Right. So I guess my question. I don't know what my question is, but
okay, let's figure it out.
Is this something very special about this particular space? It's a little bit like in I don't know, in the real line, if I choose 2 points at random with probability 1.
Yeah.
Okay. So it behaves a little bit like a continuum version of.
Yeah, I see where you're going.
That's
what I think I see where you're going. No, there seems to be an underlying principle, but whatever that underlying principle is, it will only apply to very special metric spaces that have something in common that we don't know is in common. Because on graphs, any weird behavior can happen with metric dimension. Any weird behavior. We wrote a survey, I think it's listed on the paper, about metric dimension of graphs, and it's an extremely unstable object to study. But I see what you're saying. So this is like resolving different points in the plane, and then I need to add something to resolve points that points of different size in the plane, and then points that have the same size. Well, if you look at the lower bound, the good lower bound, not the good, the more explicit, this lower bound, this is the log of x squared. So that is the distance matrix dimension, log of x squared. Yes. Let's say divided by the log of x, the number of objects. But on the Hamming graphs, if you have an alphabet of size A and you look at sequences of length k, the asymptotic metric dimension is the log of A to the k, which is x again, divided by the log of A, which is the number of different symbols. So there is a total analogy with this distance and with that metric space and this metric space. It seems too good to be so coincidental. But as far as I know, nobody has proven such a general result.
I actually have one. So what if you just in that direction? If in the octopeptide,
Octapeptide, yeah, coming graph.
if I choose another set randomly of 77 points,
Oh,
now I know that that's a good number.
yeah,
Just choose any.
yeah.
Does it result? Like, should
No.
I expect? Usually, it doesn't result.
No, at least not through the methods we did it.
Okay.
But the problem is so difficult. Well, okay. We know how to determine if it resolves deterministically, because we know how to represent the problem as a system of nonlinear polynomial equations. And there's, I don't know if you know this Grosvenor basis. So you change bases. If you change bases and zero is in the kernel, it's resolving. If zero is not in the kernel, it's not resolving. But no, this approach, the randomized version, was very different than the one for the Jaccard. And this distance is a lot simpler because the distance between this and that is the same as the distance of the first four with the first four plus the distance of the last four with the last four. It's very additive. Yeah. But it's too coincidental that in spirit, the two formulas are telling you exactly the same story. So it reminded me Kolmogorov, complexity, that kind of concepts, but I never been able to nail anything general.
So I have another question. So there is a trick in which you can codify every finite graph with just one point, which is essentially putting length to edges. You put linear, I mean, if you put like rationally independent values of the length each edge, you just need one.
Okay.
Yeah, so can you try to play this game to do the same? So, okay, you don't want to do this because it's too hard to differentiate pi from pi squared from this technique, but could you just try to somehow put distance 1/2 when you have a change between an A and a C, and 1/4 with an A and a B, and just reduce your landmarks, but without getting too much complexity on the number you get from the distance?
I would think so. In fact, we wanted to do this. We haven't done it because those type of distances arise in biology to do something called sequence alignment, to align proteins. And that allows you to have a new protein, you never saw it. You align it to known proteins. And based on the score of the aligning, if it's a good score, a scientist will say before they can do an experiment, which could take months, say probably the function of this protein is this or that or that. Yeah. Now, usually those scores have negative terms, positive terms, so they are not properly speaking a distance. But to be honest, that's another thing that I asked to one of my students. I feel I never really using properties of distance here. Like the notion of a triangular inequality, except to say it's a good encoding. But the argument of I'm dealing with a metric, a mathematical metric, didn't play a role in the construction of our analysis. Yeah.
I was going to ask, could you use other like distances, something like the Sorensen dice distance or something like that, which is closely related to the Jaccard. It's still based on binary sets.
I assume you're asking me about Kamers. Is that correct?
No. The distance instead of the Jaccard or the Jaccard distance is one minus the cardinality of the intersection divided by the cardinality of the union, right?
That's exactly the Jaccard distance.
That's the Jaccard distance. Well, the Sorensen distance you can compute. It's actually you can compute it directly from the Jaccard distance. It's a one-to-one relationship.
Oh, I didn't know that distance. Yeah.
And this distance is twice the cardinality of the intersection divided by the sum of the cardinalities of the two sets.
Okay.
And you can compute it from the Jaccard distance. And it's another one that's used. I think its applications are more in ecology or sort of presence absence of species. So
but in essence, you're saying that
if you don't need the metric, then maybe if you don't need the actual properties of the metric, I was just wondering, can you do the same sort of thing with other kinds of distances that aren't necessarily metrics?
Well, the concept of resolvability applies to any matrix of symbols. what is the least number of columns we need to choose so that all the rows are different on those columns. So yes, it doesn't need a metric properly speaking, but I thought the metric will help in part of the argument. I mean, it really was useful property. But I misunderstood your first comment because we have studied not only the Hamming distance, we have also studied the Levenstein distance, which is edit distance.
Yeah.
And there we could only tell you a resolving set, because we couldn't even get close to tell you the asymptotic metric dimension. Too difficult for us with the tools we have developed so far. Well, hopefully I inspire you rather than scare you away from your degree. Well, thank you guys. Thank you for listening.